And then, so I'll go ahead and start on tonight's lab. It's lab 6, water quality, dissolved oxygen, temperature, and turbidity. If you can't see the PowerPoint right now, let me know. But so lab 6, we're just talking about different water quality parameters. These are two of the bigger ones. Okay. If you have a question or anything, you can use the raise hand feature, or you can just type it in the chat, whichever one works best for you. I should be able to see it, but if not, just let me know. Okay, so the purpose of this lab is just to explore the relationship between dissolved oxygen and temperature. I'll go over the traditional way that we would have done it, but you will still be making graphs to visually show the relationship between dissolved oxygen and temperature. You will still have to turn in your deliverables for this week will be the 2 graphs that you make in Excel, and you'll just turn in the Excel file, and then there's 5 questions on page 59 in your lab book. You'll have to turn in a scan of those on Canvas as well. If for some reason you don't have your lab book, there is a PDF file of the entire lab manual on the homepage of this lab, so you should be able to find it there. You can either print it out or just answer the questions directly on that by converting it to a Word file. And you can turn it in that way, whichever is easiest for you, as long as you can turn it in. Once again, if you have problems with any of that, just send me a message and I will help you out. So we're going to start talking about dissolved oxygen first. Aquatic animals, such as fish, algae, marine mammals, they use oxygen to breathe just like we do. Oxygen, when it's in water, it's dissolved. It's just dissolved oxygen. Dissolved oxygen is, as far as life itself in aquatic systems, is the most important parameter, and you can tell a lot on the state of a body of water by its dissolved oxygen content. You'll see it a lot of the times as DO for short. Most dissolved oxygen is through gas exchange with the atmosphere. Through surface area, you can get a small amount of dissolved oxygen from photosynthesis. You'll see it a little bit later in this PowerPoint. So there's 2 ways, well, 2 main ways to determine the amount of dissolved oxygen within water. This first way is chemical determination. It's very accurate. It's called the Winkler method. You use a titration method. I'm not sure how much chemistry background you have, but I won't go too much into it, but you just use different type of chemicals, and the amount of, let's see, I think it's divalent manganese and iodide ions. The amount you put in determines graphically, you can look it up on a chart and tell exactly how much dissolved oxygen is in it. That's not the method we would have used in lab today. The method we would have used is this electronic determination of dissolved oxygen. You won't have to turn that in. So this picture right here, I'll show you a video in a couple seconds of how you would actually use this instrument. But on the left is your monitor computer screen. On the right is your meter. That part goes in the water, and that's where you actually measure it. These are very accurate tests as long as you calibrate it beforehand, so that you calibrate it to a known standard so that it knows exactly where it's starting and can give you an accurate measurement. If you're not calibrated right, you will never get the right answer. It's usually very quick. The percent dissolved oxygen, and then it's spit out in milligrams per liter. So let me pull up that video so we can, they're not very good videos. Let me, but if you can't hear it, let me know. I'll see what I can do.
Hello. This is a brief introduction to the Hawk LDO-101 dissolved oxygen probe. In conjunction with the Hawk HQ40D multimeter, this setup allows us to read the dissolved oxygen concentrations of a water sample, as well as its percent saturation of dissolved oxygen. The principle behind this is that of luminescent dissolved oxygen. For more information on this method, please contact your instructor. Here, on the probe interface, the meter, we see that there is a large display number that reads in milligrams per liter. This is our dissolved oxygen concentration. We also see smaller numbers on the side, which read the temperature in degrees Celsius, the percent dissolved oxygen saturation of our water sample, the barometric pressure, and the date and time. This setup allows us to read the dissolved oxygen concentrations of a water sample, as well as its percent saturation of dissolved oxygen. The principle behind this is that of luminescent dissolved oxygen. For more information on this method, please contact your instructor. Here, on the probe interface, the meter, we see that there is a large display number that reads in milligrams per liter. This is our dissolved oxygen concentration. We also see smaller numbers on the side, which read the temperature in degrees Celsius, the percent dissolved oxygen saturation of our water sample, the barometric pressure, and the date and time. You will also notice that there is a little graph icon in the upper left-hand corner with an OK next to it. This ensures us that our probe has recently been calibrated. This probe is set to read instantaneously, meaning that there is no need for interface with this meter aside from placing the probe into our desired sample solution. On the probe itself, you can see here this silver button is the temperature sensor. You can also notice that the probe lights up in this blue and red alternating flash, and that is what allows us to read the luminescent dissolved oxygen. In order to properly read a sample, we need to make sure that our probe is clean before we place it into any sample. We'll do this by rinsing it off with deionized water, which is just pure water, and we want to make sure.
Okay, so the videos are not very good, but it's the best we have right now. Basically, the gist of it is just that you put this little meter in the water. You might have seen the little silver ball. Just make sure that's under the water. That'll give you the dissolved oxygen content, and it will give you the temperature. The way it works, just briefly, is you might have seen the flashing blue and red. That's a oxygen permeable membrane. Once you put it in, the oxygen flows freely back and forth, and based on the temperature and other things, the instrument calibrates it quickly and spits out the number, and it's usually very accurate. You would have used them a couple times in this lab. Honestly, I don't know how many times, unless you go into a scientific field, you'll encounter them in life. But if for some reason you want to watch those again, that video is linked to the Lab 6 page on Canvas. So we'll keep going. There's a couple different factors that affect dissolved oxygen content: air, water, gas, transfer temperature is the big one we'll be testing today. It has a direct relationship. You'll see in the data and the graph that we give you and the graph that you make. Dissolved oxygen is extremely limited by temperature. The two main things that affect dissolved oxygen is going to be your temperature and atmospheric pressure. I think I'll just talk about it here, but so when we talk about saturation points and saturation, when you reach saturation, it's the absolute maximum amount of dissolved oxygen that you can have at the given temperature and the given atmospheric pressure. So you'll see later how temperature affects that. But if the water is saturated, it cannot get any more oxygen naturally. You can get supersaturation, which is you'll get a higher dissolved oxygen content than your saturation limit. It's kind of like overshooting a carrying capacity that we saw in lab 2. This will always autocorrect. The easiest way to get supersaturation is through this next bullet, or black bullet, is turbulence. So since it does have air, water, gas transfer, if you shake up your water, more water particles are coming in contact with the air, so they absorb more oxygen. But that's just temporary, so that's how you can get supersaturation. So if you think of a waterfall or rapids, those are areas that are normally going to be supersaturated. Yeah, let me put it in the slideshow for you guys. But those are areas that are going to be supersaturated, but that always balances out. The next is sediment oxygen uptake. This is going to be usually very small. We'll address it more in a slide or two, but this is just going to be bacteria content that uses oxygen to survive, animal plant respiration, photosynthesis, same thing. And then this little bullet on the bottom right is pretty important. Fish generally need 5 to 6 milligrams per liter of dissolved oxygen to thrive. I believe it's 4 is when they start having problems. And then if it's less than 3, then fish and other life will start to die. So sediment oxygen uptake, this graph just kind of shows you that the dissolved oxygen, which are the floating red O2s, are taken up by bacteria that resides in the sediment by bacterial respiration. I'm not sure why I won't go to the next slide. Okay. I'm just going to do it from here because that'll be easier. Does anyone have a problem seeing the slides? Okay, cool. So animal and plant respiration. This is the chemical formula for respiration. You have glucose, C6H12O6, plus 6 moles of O2, and that is converted into CO2, which is breathed out, water, and then heat energy. Also, I think it's ADP, but that's not really something we need to focus on in this class. All animals, fish, bacteria use this as well. They're converting dissolved oxygen into CO2 and H2O. Photosynthesis is pretty much the opposite. All your algae will use this. It's going to be 6 moles of CO2 plus water and light energy, and they turn that into glucose and 6 moles of oxygen. The red just means that it is a gas and that it will rise out of solution. This is just a little graph to show you how dissolved oxygen fluctuates. This is in a pond. As you can see, when it's darker, the dissolved oxygen content will be lower because there is no photosynthesis going on. And then around 6 p.m., usually around sunset, your dissolved oxygen is going to be the highest because you have had these organisms using photosynthesis throughout the whole day, so you have the highest concentration at night. This is a graph. You'll make one today with the data that you download, but this is generally the relationship between dissolved oxygen and temperature. They are directly linked. We don't really need to get into vertical stratification. That's a little too deep for this one. Low dissolved oxygen, low dissolved oxygen does lead to fish kills, but it doesn't necessarily lead to algal blooms. We don't really need to get into that. That's kind of a higher level concept, but algal blooms cause low dissolved oxygen. It's not necessarily because of it. Aeration, this is just like the turbulence. This water is being shot out. I'm sure everyone's seen these little fountains and retention ponds or anything. It just is a way to aerate the water, increase the dissolved oxygen content by increasing the contact with water molecules and the surface air. That's not important. You might see these fish eat algae. I think that's really all we need from. Well, this is going to be important for the second part, is turbulence or turbidity. So there's no real slides for turbidity, so I'll go over it now. Turbidity is another important water quality parameter. It is basically just, in simple terms, it's how clear your water is. If you have a higher turbidity or it's more turbid, it's going to be very cloudy. It's going to be hard to see through the water. Let's see. So the lab that we would have done today would have been simulating what happens after a first flush event, after the first rainfall of a season on a construction site. We would have used a turbidimeter. Unfortunately, we have one more of those videos, so I will go ahead and play that now. It just is showing how to use the turbidimeter. Let me pull that up for everyone.
Hello, this is a brief overview of the Hawk 2100Q turbidimeter. This instrument allows us to read the turbidity value of a water sample. Turbidity is a word used to describe the cloudiness or haziness of a sample of water. On our display screen, we can see a large number here that depicts our turbidity value in NTU. This stands for nephelometric turbidity units. A nephelometer is another word for turbidimeter. Also on our interface, we can see the date and time represented. We also have this graph symbol, graph icon, with OK next to it. If that is present, then we know that this instrument has recently been calibrated and is ready for use. Also on our interface, we see a button that says Read. If we were to press this button, then that allows us to take a reading of our sample. In order to prepare a sample, we will take a sample in a vial, specially designed for this turbidimeter. To prepare it for reading, we take this silicone oil and place less than a drop of it on the surface of our sample vial. We then take a dry microfiber cloth and rub the silicon oil into the surface of our sample vial. The silicon oil has the same optical properties as the glass that this vial is made out of. That allows it to fill in any scratches or marks and wipe off anything like fingerprints that may be previously existing on the surface of this vial. We also want to invert our vial multiple times so that it is well mixed and fully representative of the sample. We then find this arrow on our vial, open up our turbidimeter case, and place the vial inside, matching the sample vial arrow with the arrow on the turbidimeter. The sample that I'm reading right now is a deionized water blank. That means there should be very little, if nothing else, in this sample vial, and we should get a very low NTU reading. I snap the vial shut and press read. Once the turbidimeter stabilizes, it gives us the value of 0.04 NTU, which makes sense as there should be very little, if nothing else, in this vial. It should be very clear. Taking it out, we observe that this vial is indeed very clear, and this turbidity reading matches our eye test, simply looking at the vial. For comparison, here is a standard of 800 NTU. When I invert this standard, we can see that it is very, very cloudy. You cannot see through it at all.
Okay, so that's the turbidimeter. Once again, I know the audio is not great. It is linked to page 6 if for some reason you would like to watch that again. But basically the gist of that is the turbidimeter measures how much light passes through the sample, and by that it determines clarity. So the lab that we would have done is you would have had 5 different samples. You would have had control, which is just deionized water, which theoretically should be a NTU of 0 because it is absolutely nothing except clear water. You would have had samples, and then 4 samples with 4 different types of sediments, and those would be sand, loam, silt, and clay. And you would have taken them after to simulate before the storm event. You would have taken them immediately when you got to class, written down how many NTUs you got, and then each sample you would have shaken up, taken another reading, and that would be immediately after the storm event, and that would simulate your first flush event, so the first major rainfall of a season, and the construction site washing away all the loose sediment into a river, kind of like how this picture shows. It would be simulating taking a sample from the river on the right and testing that, and then we would have let the sample sit for an hour while we did the DI or dissolved oxygen portion, and then you would have taken another reading after 1 hour had lapsed to see how quickly it takes different types of sediment to settle. Let me look and see if there's anything else. That's not really important. All right, so that's it for the PowerPoint slides. There's a couple things I want to show you real quick, just regarding sediment. So there's generally 3 different types of, can everyone see like a triangle on the screen? Let's see, I'm not sure. Okay. So there's 3 major types of sediment or soils. I don't know if you guys cover this in lecture, but if you can see my mouse, you have the three main types of clay, silt, and sand. And we would have tested each of those. And this matrix right here just tells you which of these major categories your sediment falls in based on the percent composition of what is found there. Clay is most dominating, silt less, and then sand even the least. So the major difference in all of these types is particle size, and I will show you a little graph that shows you the different particle sizes. So if you start at the top, we wouldn't use these, but obviously gravel is going to be bigger. Everyone's seen sand, I'm assuming. You can see individual particles. And then silt is even smaller, and then clay is your typical mud. Here's a visual representation of that. Sand, you can see individual particles. Silt is what you would normally think of as dirt. And then this is red dirt, clay, but mud. It's extremely tiny particles, and those are also, they have chemical attractions between them, but we don't need to get into that for this class, really. Hold on, I'm having trouble. Okay. And then, so basically what we want you guys to pull away from this is once you look at the data. So now we can go ahead and, if everyone will go to page 6, go to pages on Canvas, go to water quality, lab 6. We can go ahead and download all the data. But basically what you're gonna wanna get out of this lab as it pertains to turbidity is that your larger sediment particles are gonna fall out of suspension quicker because they don't have much of a attraction to each other and gravity works harder on them. So as you'll see, sand, silt, and clay are all going to have extremely different NTUs after this. They're all going to be very high immediately after, but once you give them time to settle, they will rebound more quickly. Sand will rebound a lot quicker. It'll be a lot clearer. Clay will still be extremely high. Clay usually takes about a day to settle just because it is so hard to have those particles fall out of suspension because they weigh practically nothing. That's the main part of this whole turbidity. If you go down to the bottom, here's the 2 videos, but if you go down to this bottom, it says download MS Excel file with data to use for completing this lab. Go ahead and open it up. This is what you'll be using, and if you don't have Excel right now, you can just kind of watch and follow along, and then once you do get Excel, or if there's an alternative, then you'll know how to use it. So let's see. Stop that. All right, can everyone see my Excel now? Can anyone not see it? Okay. So up here, once again, you'll have to enable editing once you download it. Okay. So you should get this Excel sheet with everything filled out. This top 2 bars or rows will be your temperature and dissolved oxygen data, and this chart down at the bottom will be your turbidity data. All you need to do with this is you'll need to make two graphs, one showing the relationship between temperature and oxygen, and you'll use this, you'll make it, put it on a scatter plot, and then for your turbidity data, you'll put them into a bar graph. So I'll show you how to do those real quick. You can do them along, you can do them later, but so what you'll want to do is you'll want to highlight everything, including these labels, temperature and dissolved oxygen. You'll go up here to insert, you'll go down here to scatter, you'll click it, you'll click this first one, you just want to scatter, and then that's going to be your graph. You'll have to change this title. Make sure you add axes titles. You'll need to change, so you can kind of guess just by looking at what the data, where the points are, or the axes, which is which. Your bottom is going to be temperature, your left side is going to be dissolved oxygen. You'll need to put these, label them, you'll need to change the chart title, and then that's all you have to do for the dissolved oxygen chart. I'll move that out of the way. And then so for this next one, all you need to do is highlight all of this. Make sure you get the before storm, after storm, and 2 hours after storm. Get all of the data. You'll go to insert, and then you'll go up here all the way on the top left, insert column or bar chart. I'll do this first one. Your legend should already be filled out. Once again, you'll need to add your axes titles. You'll need to, you can do that here, or I know Macs do not have this option over here. You can go all the way up here on the top left. It'll be add chart element, and then axes titles will be right there. You'll just have to do it twice. And then for this next part, to get for down here where it says 1, 2, 3, 4, and 5, you need to put the labels of what those actually are on there. So to do that, on a PC, you should get this chart filters. On a Mac, it'll be up here. You can hit select data. I'll do it for the PC. You'll click that, click down here for select data. Both of them should pull up this screen if you clicked it through the filter or if you clicked it up here through the top. Right here, you're just going to want to change your horizontal category. Everything else should be fine. You'll just hit edit and then go right to left, and as you can, and then you hit OK. Okay, and then as you can see, it puts all of them in the right location there. And then all you have to do is change your axes titles and your chart title, and then your graph is complete. If you have that, then you'll get full points for the graphs. That's all you have to do for this Excel. It's really easy. You can go ahead and do it now. If you need me to walk through the steps again, just let me know. You'll be turning in this Excel file once you save it with the completed graphs, and then you'll answer pages or the questions on page 59, and that's all you'll be turning in for today. So does anyone have any questions or anything? Yeah, I'll do that again for a Mac. So I'll delete these real quick. So if you're doing it on a Mac, it'll look a little differently than I'm going to show you, but all the buttons should be in the same place. The only thing that might be a little different is the screen, but I'll point that out when we get there. The data in yellow, it should be provided for you. If it's if you downloaded it and all the yellow was blank, then you downloaded the wrong Excel file. You downloaded the Excel file at the top of the Lab 6 page. What you'll want to do is you'll want to re-download the Excel file at the very bottom. That one will give you these numbers. So to do the dissolved oxygen scatter plot, you just want to highlight all of this. Well, actually, you don't even have to do the labels. You can just do the data. You'll go to Insert right here. And then right here, this one on the very bottom row, insert scatter X and Y. You'll just do this first scatter plot. Click it. It'll have your chart title. All you need to do, so you'll have this, and then on a Mac, you'll want to be up here in this chart design tab. You'll go over here to select data. Oh wait, no, sorry. This is for the scatter. You'll go all the way over here to the left, and you'll go to add chart element. Axis titles will be the second one. You'll want to put your horizontal, and then you'll have to go back and you'll put your vertical. And then you'll have all of your titles already right there on the graphs. All you need to do is customize them so that it actually identifies what each part of the graph is. And if you do that, you'll get full points for that. For the second one, for turbidity, this one you have to, well, you don't have to do it now, but it'll make your life a little bit easier if you drag all the way from the left, including before a storm, after storm, and 2 hours after storm. Include these three, and then get all of your data. Once again, you'll go to Insert. You'll be putting a bar graph. So this one will be a column. You click this, it's going to be the top left. You can just do this first one if you want to get a little fancier with it. You can do a 3D, but I'm just going to do the simplest way. So now you'll have this, you'll have your legend, which since you included those three is already filled out the way you want it to be. You have your chart title. You need to add your axes titles, just like the others. So you'll go to add chart elements. And then now you have your axes titles down here. And then to get labels on which columns are which, all you need to do is you will go up here to select data. You'll click that. This page will look a little different on a Mac. Instead of it being side by side, I believe it's up and down. It's still going to say this exactly. I believe it's just a line that looks like this, but I think it's towards the bottom. Once you find that, you'll just click Edit. And then all you'll do is you'll highlight the 5 things that you want. And as you can see, it will pop up right there on the appropriate columns. You hit OK, OK. And then that's it. You just need to change your axis titles to say what is what. And then change your chart title. And that's all you need to turn in. I believe I went over everything in the questions on page 59. Question 1 is just turning in your Excel file. And then the other ones we kind of talked about. If you want to log off, do the questions on your own and turn them in, that's fine. We also have a lot of time left in class. If you want, I'm still going to be on here. If you want to stay on, do your questions, and you can ask me questions. It's whatever's easiest for you. It just will be due like normal next Monday before 5:15. So whatever's easiest for you guys.